All right, well, we are covering chapter two, and this is thermal processes. One of the things that we're going to be looking at today is a Stirling engine. Now, I'm going to set this Stirling engine on top of a glass of hot water. I can start with, I can flip this. You can tell it goes around and around a little bit, and then it just stops. Why doesn't that just keep going forever when I flip that propeller? Friction in the air. There you go. There is a loss of energy, friction, the air. It's more than the air. In fact, the air is probably less of friction than the bearing points. In other words, where anything touches, you're going to have friction with movement. We try to eliminate that in really fancy systems with magnets. You put a magnet and a magnet that repels each other, and you can levitate things. Um, what's the heaviest thing that you think we could levitate? Trains, and that a lot of people don't think about it, but trains. Oh my gosh, how heavy are trains? But if we can keep the train up off of the tracks, you don't have the friction of those wheels. You don't even necessarily have to build the track. You just have to make sure that the train itself is held into place with magnets, but the friction would be extremely low. So as that train, if it was on magnets, would continue to go through the air, you'd still have air resistance, wouldn't you? And so they are actually have tubes that they will vacuum the air out of in order for a mag lift train to have a lower resistance. If you eliminate the air resistance and you eliminate the frictional resistance, can you guys think of anything that we have basically eliminated the air and the frictional resistance from and is moving right now? About a satellite around the world, around the whole Earth. There is virtually no air friction resistance. And I say virtually because there always is. Even in the darkest recesses of space between galaxies, where there is nothing, there is the equivalent of approximately one atom every cubic centimeter. It's normally hydrogen or oxygen or helium, very primary element. Yes. So there's always something, and when that satellite hits even one atom, it's got to move it, which slows down. That's resistance. That's one of the things that talks about this is there's always a loss. But when heat is concentrated in one area, it wants to flow. It wants to get out of that area. And so once it's given a path that it can get out, it does get out. It will move. All right. And we can actually extract part of the energy from that movement of heat. That's what a Stirling engine does. It has an area of high concentration of heat and it has an area of lower concentration of heat. What's the temperature in this room? Anybody? 70 probably. The thermostat's probably set at 72. It's probably a little warmer than that. She just microwaved this glass of water for 3 minutes. When she first brought it in, it should have been at boiling temperature. What temperature would that be? 100 degrees Celsius. If we're talking about Fahrenheit, because we gave our room temperature in Fahrenheit, do what? 212, yes. Now, if we were really talking scientific, remember, this isn't a theoretical class. What do you think the actual boiling temperature of water is here at the elevation of about 1,000 feet elevation in Neosho, Missouri? Do what? Lower than 212. The higher elevation you get, the lower pressure, and the lower the pressure, the lower the boiling point. And right, and I'm going to tell you a story that will make you remember this forever. I went to the University of Arkansas. Times were different. We were not as politically correct back then, and I took a physical science class. The class had about 200 people in it. There was a lot of people. The professor wanted us to pay attention. There wasn't internet that we could go research the same as there is today. So we needed to really learn this material from the book and from his classroom. And he was talking about pressures and boiling points, and he had this big jar. It had a funny looking thing on the top of it that looked like it was some type of a pump. He took the lid off, he poured a gallon of distilled water into it, and he put the lid back on it, and then he began to pump. As he did so, he began to talk to the class. There was one particular female that sat at the front of the classroom, and she always dressed to the hilt. I don't know if she had fashion design immediately after or physical science, but she was always dressed like she was going to the club or going out or something immediately after the class. And so, as soon as he got all of the air pumped out of this container, he had basically created a vacuum. He asked the young lady from the front of the class, and I need a volunteer. Could you please come up? And she put her hands on the side of the container. And immediately her heat in a vacuum created enough energy for phase change. What is phase change? No, it's where a solid would turn to a liquid or a liquid would turn to a gas. It's where you change from one phase of material to another, and it takes a lot of energy to phase change. We're going to talk about that in just a little while. Well, when she put her hands on there, her heat input was enough to phase change the water, a small amount of it, from liquid into gas, and it began to boil. And he stood back and he said, "Girl, you're hot enough to boil water." Now, today, that'd probably get me in trouble if I singled out a female in class and said that, but it stuck with me like, what a pickup line. If you just, I'm going to bring my science kit to the bar, I'm going to set it up on the bar, like, hey, you're hot enough to boil water. No, there's just a low enough pressure in this situation that anybody could boil water. All right. And so, obviously, we've had some heat energy movement here. Can anybody try to explain how this propeller is still spinning? How has this overcome the friction of the air and the bearings in order to continue to move? Yes.
The engine is made the heat going from one pressure to the next. It's turning that.
It is going from one pressure to the next. There is nothing physically moving through here, because heat is what? What is heat? Movement, yeah, kinetic energy, the movement of particles. So the particles here are bumping into the particles here, and these are bumping into the next ones. Nothing is physically moving except energy. So how am I capturing that energy? Well, I have a chamber in here. I'm going to pass this around, and I want you to spin it and look at this chamber. The chamber actually has two components. It has one that's a foam disc. When that foam disc is downward, all of the air in that chamber is at the top. And that air is relatively cool, or it's cooler, because the top of the chamber is exposed to the outside and the outside is cooler. So that air would get cool. Okay? When air gets cooler, it condenses. So it creates a lower pressure. When it does so, there's a little bladder at the top that's rubber, and that bladder pulls in. But that bladder basically has a rod on it that begins a momentum cycle. Well, that momentum makes the large disc rise. And whenever it rises, it pushes all of the air that was at the top down to the bottom. And at the bottom is a hot material. That hot material now makes the air expand. That hotter air makes that little bladder expand, which pushes that rod up and continues the cycle of momentum. That rod rising pushes the disc back down. Now, in my brain, I would think it would move like flump, flump, flump. You guys ready to see how fast a Stirling engine could actually spin? Take your guess. How many RPMs can a Stirling engine, just from heat, spin? 1,000? 8,000? Like, I've never owned a vehicle that can spin 8,000 RPMs. I had one that would redline at 7,000 RPMs. But 8,000, I mean, you're talking like real, like, sports car type there. I mean, like motorcycles. Yeah. Motorcycles a lot of times redline at maybe 12, 13,000. I've heard of somebody maybe getting to 15 or 16,000 with a motorcycle or something like that. 13, yeah. So the RPMs, the revolutions per minute, is one of those things that it adds a lot of friction, adds a lot of heat. The faster that you go, you reach these theoretical limits. Because things have to change direction. It's got to stop, and it's got to come back, and it's got to stop, and it's got to come back. So, Slide this one on over. No, I didn't want to do that. Where did we go? Where's my mouse? So I like this guy's videos because he tries to break things.
And I'm not just showing you this engine to show you this engine. I actually have a plan in mind. If you've seen any of the previous episodes, you know that I like pushing things to their limit. And this is going to be no different. I want to see what the maximum RPM is that I can get out of this engine with the intention of blowing it up. But before I do that, I want to show you how this engine runs, the way it comes if you buy it, and then move into the high RPM runs right after that.
Nothing but heat. All it's doing is moving heat from one section, this bulb, through into a coolant. This is a generator to generate electricity. So basically this is taking heat energy, turning it into kinetic energy, taking the
As you can see, this engine's pretty cool. It functions
a belt
perfectly.
and running to a little generator.
It's a real engine. In my opinion, this is an awesome little engine for the price.
Tiny scale of what a huge grid-sized generator would do. So he's going to do some advertising, and I'm going to skip. No clue. But here's he's got a blowtorch, and we're going to get an ad here. They got to make us pay for it for a second. So I would guess probably $600 to $800. But you can watch this. It's advertised where to buy these.
All right, well, that answers that question. Looks like I got about 4,000 RPM out of this engine, which doesn't sound like a huge number, but if you think about the fact that most Stirling engines run between 400 and 600 RPM, with certain designs getting up to 1,200 RPM, well, 4,000 starts sounding pretty impressive. This is kind of unfortunate. I mean, we have some damage, but not really the damage I expected. I mean, the whole engine is pretty hot. This whole thing is hot, even this. But the weird thing is that the cylinder isn't damaged, but the piston has melted. If you look inside there, the piston is melted, but the cylinder's undamaged. And let me tell you, this really surpassed my expectations, and it's definitely worth the price that they're selling this thing for, because if it took that, I mean, man, it's definitely worth its weight. Looks like a little icicle. Yeah, I think this would have stood running. Just one more time, let's see what's inside there. Doesn't work out, I'm still going to post it, because sometimes...
There's one other section in here that it shows slow-mo that I like.
Subscribe, check out the notification button.
There it is. All right, so how do I get you to remember this? This is how we were going to power all of our spacecraft before we invented solar PV. Because we can take a parabolic trough, a dish, point it at the sun like a satellite dish, and reflect all of that solar radiation directly onto one point. Let me tell you, gentlemen, space is colder than my ex's heart. So if I have a really, really cold place, and then I have a highly concentrated hot place, heat's going to flow through rapidly. I can use this to produce electricity, to compress air, anything for motive force. Why would this be inferior to solar PV? There you go. Everything that has moving parts fails in time. Number two is it wears. You put bearings, and no matter how great they are, eventually you're going to have wear and tear. That's one of the reasons that if we can keep things from touching, like we use lubricants or magnets to keep them from touching, they will last longer because then you're going to have less wear. But even air causes significant damage over time. Has anybody heard of the term cavitation?
Oh yeah, all of my teeth.
Your teeth. Okay. Not quite the cavitation that I was talking about there. If you have hydroelectric generators, they have giant turbines. If you have wind turbines, they have giant turbines. Over time, air that gets trapped behind the blades, even in small amounts, will actually wear away the metal. Cavitation is the wearing of any component due to just natural rotational fluid friction. All right. So a little bit more detail about how it works. I know this may be a little cheesy. You guys have it's probably been middle school since Bill the science guy has needed to explain something to you. But hey, he does it better than me.
Warm water is a source of heat. There's a special type of engine, a Stirling engine, named after the Stirling brothers, who invented it, got a patent in 1807. The heat from this water is warming the bottom plate of this engine. Give it a little nudge.
This is the same style as the one that we just saw.
Now notice there are two pistons. There's this little one up here, the primary, and then there's this big one down here, the secondary. As the heat from this water warms the bottom plate, it makes the air expand. The expanding air drives the piston. So this is a way to convert the energy of heat into what we call mechanical work, or making something spin. And the extraordinary thing about Stirling engines is they're so efficient. It's just a little bit of hot water. And look how fast it's making the wheel go. Now watch what happens when we take the same Stirling engine, running clockwise, and put it on another beaker, but this one's full of ice water. In just a few seconds, the Stirling engine will slow down because it's lost its source of heat from the bottom. But now, it will run the other way. So there's an old joke in science. A thermos bottle keeps cold things cold and hot things hot. How does it know? Well, the reason it knows is because, in a sense, in science, there's no such thing as cold. There's only the absence of heat. So this is still a heat engine, and it's running off of heat. But the source of heat now is the room. The air in this room is warming the top plate, and heat is now flowing down through the engine instead of up through the engine as it was over in the source of hot water. The Stirling engines have been proposed for all sorts of things. In the early...
All right, guys. I think that we have the concept. Thank you, Bill. So, how does heat move? There's three mechanisms that heat goes from one place to another. And that's going to be a very, very big part of today and this chapter. There's three mechanisms. Who can name one of those mechanisms? Radiation. So an example of radiation would be the sun is very, very hot. Space between the sun and the earth isn't that hot, but the radiation passes through that space and heats the earth. Radiation is one of the three mechanisms. Can anybody name another one? Conduction. And our third is convection. Okay, so we got conduction, convection, and radiation. Conduction is the easiest one to understand. If you have a hot parking lot and you walk with your bare feet on that hot parking lot, the heat will conduct from the parking lot into your feet, and you will feel it and it will be hot. Now, there is one concept that has been taught to you in the past in theoretical classes rather than truly scientific classes that is wrong. and I will count it wrong, and I will trick you into trying to get you to tell me it wrong. And that is, heat flows from where to where?
Higher energy to lower energy.
I heard higher energy to lower energy. I heard something else. There we go. That's the concept that you've been taught your whole life, is that heat rises, and it is totally and utterly wrong. Heat flows from hot to cold. Now, occasionally I'll have somebody like, no, heat rises. Okay, let me get a cast iron skillet and you put your hand on the bottom of that skillet after it's hot. Wait a minute. If heat rises, the heat can't go down and get you. It's going to rise. Why is it still burning your hand? Because your hand is colder than the metal pot, and so the heat is flowing from the metal pot into your hand. Hot air is less dense than cold air. Therefore, hot air rises. And that's the reason it's taught as a misconception, is everybody wants to say heat rises instead of adding that key word in there of heated fluids rise within their environment. That is convection, gentlemen. If I was to, let's say, have a heating element in my convection oven, and the heating element is 800 to 1,000 degrees, and I put a little thermostat in there that measures the air temperature, and at 350 degrees, it turns that heating element off, and at 351 degrees, it turns that heating element on. All right, you put cookies in there. The cookies are 75 degrees. They're room temperature. 20 minutes later, you pull the cookies out of the oven. The air stayed the same temperature nearly the entire time. The heating element stayed the same temperature, on and off, on and off. Where did the heat go? The heat went from the heating element to the cookies, but it used the natural convection of the air in order to move that heat. That is convection. So we have conduction, convection, and radiation. Convection is by far the hardest one to understand. So conduction is the easiest one to understand. If you're worried about understanding radiation, let me give you an easier example, and it will help you also understand convection. When's the last time you guys were sitting around a campfire in the dark? Now, pandemic slowed down the number of campfire gatherings I have gotten to have in my life, but earlier this spring, or earlier this year in the spring, we had a nice campfire, and as I sat around there, I could feel the fire. I could raise my palms and I could feel the fire. Yet if I were to measure the air temperature, it's the same on this side of my hand as it is on this side of my hand. That fire is not heating the air. In fact, that fire is taking the air, using it in combustion and making it rise. So you're going to have a breeze normally from behind you coming to the fire, all wind taken into account as being gone. So in fact, the air that's coming from behind you would possibly be even cooler, okay, as it came through. So you are not feeling convection. You are feeling radiation, all right? If you had a hot poker that you left in the fire, the end of that hot poker that's not on the fire would still get hot because of conduction. It would conduct the heat down the hot poker. The air that is being heated and is rising, that would be convection. So sometimes convection is easier to think of as a global scale. At the equator, where there is more annual sunshine throughout the year than other places, then their air gets heated more, which makes it rise. And at the poles, where it is colder, their air sinks, and it creates a natural air current. We sometimes might refer to it as the jet stream, but the whole physics behind the jet stream is convection. Air that is heated, that is rising, air that is cooled, that is sinking, and the distribution of that uneven heating of the Earth's surface. So, we measure heat in a couple of different ways. You might want to try to be thinking of a calorie, okay? Calorie and a BTU are the same thing. You also might be thinking of temperature, like Fahrenheit. Don't we measure heat and temperature? No, no. Temperature is a measurement of the heat that is contained in a substance, and Fahrenheit or Celsius or Kelvin is the scale that we would use to measure that heat. Heat is actually measured in BTU units. What does BTU stand for? There you go, British thermal unit. Now, we're not using that number because this is a British book or a European book, or because America was colonized by Great Britain. BTU is one of the units that is internationally recognized. The other is the calorie. Where do we think of the calorie, though? Why do we tend to not talk about calories? It's still turned into heat energy, but it is more like food energy is what we associate it with. You can totally do conversions from the BTU system of English, okay, British thermal units. 1 BTU is equal to 1 pound of water raised or lowered by 1 degree Fahrenheit. All right, so let's make that make sense. I have 1 pound of water. How much is a pound of water? Anybody? That's kind of like saying a foot is 12 inches. How about volume wise? Two. A cup is 8 ounces, gentlemen. I can tell that we haven't spent a lot of time cooking. So a cup of fluid is 8 ounces. So 2 cups would be 16 ounces. Those are referred to as fluid ounces. And they are the exact volume of water based on the weight of water. In other words, 8 fluid ounces of water weighs 8 ounces. 8 fluid ounces of milk, would it weigh 8 ounces? No, because it's not water. There's other things in it. So it has a different specific gravity, okay, a different density, in other words. All right, so now we've kind of understood what 1 pound of water is. That's 2 cups of water. If it is 70 degrees and I raise that water to 71 degrees in those 2 cups, I have expended 1 BTU of energy to do so. If I have that water and it is 90 degrees, and I put it in the room until it lowers itself to 89 degrees, it has expended 1 BTU of energy into the room. Does that make sense? Yeah.
So either way, if it goes
Mhm. The water expended 1 BTU of energy. If it went from 70 to 71, then the room expended 1 BTU of energy to heat that water. But yes, it's always 1 BTU up or 1 BTU down. Yeah. Whether we put that negative in front of it or not is depending on our perception of what we're measuring. So, but good question. Yeah. Any other questions on BTU? What is it? So when we start to talk about thousands and tens of thousands of BTUs, you'll have an idea of what kind of energy level we're taking. The first time that I studied a BTU, it was calculating BTUs in peanuts. It was in a high school class, and they had us build these little stands out of paper clips. Your stand had to hold your peanut, and then you had to measure your temperature of your water. There was 8 ounces of water in there. You would light your peanut on fire. Peanuts burn very well, in case you didn't know that. And then you'd slide your peanut under your water and you'd measure the temperature rising in your water to understand, wow, this little peanut contained 23 calories. Wait a minute, calories. What's the difference in a calorie and a BTU? So the calorie is the metric system. Guys, trust me. If you've ever used the metric system and the American or the British system, the metric system wins 99% of the time. Much of the solar industry sticks to the metric system. We are always talking about square meters rather than square foot. We are always talking about kilowatts, using the metric system or the SI system. All right. So the calorie in the metric system, we have a little calorie and then we have a large calorie. So that works well because of the grams system and the water system. Now, you've probably not heard this, some of you might have, but can anybody tell me how much volume 1 gram of water is? So there is true logic behind all of the scientific notation system. If I were to take a centimeter square and I was to fill it with water, that is 1 gram of water. That's how they based the centimeter on. So very easy to go anywhere and reproduce that measurement. All right. And so 1 gram of water, 1 centimeter by 1 centimeter, raised 1 degree Celsius is 1 little c calorie. 1,000 of those little c's becomes a big C. Sometimes it's just used as a K for kilocalorie. Guys, you'll be happy to know we're not going to do too much of these. Like, I'm not going to ask you to convert calories to BTUs or back and forth. I just need you to understand the concept of what a calorie is. It really is a measurement of the heat that your body can extract from the lunch that you just ate. All right. In fact, we can measure how many calories you burn based on your body temperature and its area in order to keep that mass warm. That's how a body bug used to function: is measure your temperature and your activity level. They've got more advanced algorithms now. All right, what is specific heat? So specific heat is the amount of heat energy that a substance can store based on a certain amount of area. Let's use water, for example. If I had 1 pound, 2 cups of water, all right, and I need to heat that up by 10 degrees. If I also had 1 pound of brick and I needed to heat it up 10 degrees, the amount of heat that substance can store within it, that is the specific heat of a substance. Anybody want to guess what substances, or from your reading if you've already read, what substances have the highest specific heat? Metals? Anybody want to differ? Alkaline metals? So do you think metals have a higher specific heat than stone? You think stone would? So now I made another suggestion. Somebody's changing their mind. Wasn't a lot of confidence in that, huh? Well, how about water? Does water have a very high specific heat? No? No? The highest specific heat is water. Water is dramatically higher specific heat than stone or metal. Yeah. So your book has a couple of different charts on it, but the specific heat is the amount of heat energy per unit of mass to increase or decrease the temperature of that substance. Specific heat for BTUs. And again, this gets into some math that if you guys are going to end up taking a solar passive design class in a 3-hour format, you end up learning how to calculate how much BTUs were gained or lost based on the specific heat of the material and the mass of that material. The reason that's important is to know how much thermal mass that you need for your greenhouse or for your home, so that during the daytime you can heat it up, but during the nighttime it can release its heat to keep freezing or unpleasantly cold temperatures from occurring inside of your home. All right, so the laws of energy conservation and the laws of thermodynamics, we talked a little bit about those last week. First law of thermodynamics is what? There we go. We can't create energy. We can't destroy energy. We can make it change forms. And mass is one of those forms of energy. All right, we can turn mass into energy, and we can turn energy into mass. We're not good at that yet. Someday. So energy can't be created nor destroyed. The second is a little more complicated. There's always inefficiencies. In other words, if I could put this to have a perfect engine, if the second law of thermodynamics didn't occur, I'd flip this and it would spin forever. But we can't do that because there's always losses within our systems. Frictional losses, heat losses, resistance losses. Always somewhere is there losses. So phase changes. We mentioned or we touched on phase changes just a little while ago, but that is where a solid would turn into a liquid would turn into a gas. Is it possible for a solid to turn directly into a gas?
Yes.
Yeah. Can you give an example?
Dry ice.
Dry ice. That's an excellent example. You've got carbon dioxide, I believe, isn't it? It's cold enough that it's solid. You don't open your cooler and find a puddle of carbon dioxide in there. It just goes directly from that solid dry ice to gas. All right. You have another one?
What kind of explosion would make that happen? Oh, it's not an explosion. It's just I'm not necessarily dry ice. Is there an explosion?
I don't know if there's a term that would specifically identify an explosion would make that happen. In our industry, if you have enough electricity passing through a metal, let's use copper as an example, it can flash that copper from a solid directly to a gas. So if you have water and it goes from a liquid into steam, it takes up 1,700 times the space. There's 1 cubic foot of water turns into 1,700 cubic feet of steam. I believe that when you go from a solid in copper to a gas in copper, it's more like 30,000 times the expansion rate. So you can take a tiny bit of copper wire and have that amount of copper flash into a gas, and that creates the explosion. You have a massive expansion of the gas. It blows the person backwards. The flying debris that it impacts can impact and create shrapnel, basically. But it's fairly rare because it takes a tremendous amount of energy input to flash it from one solid through a liquid phase to a gas phase. All right. The one thing that people don't realize is that to change phases requires a tremendous amount of energy input. And that's what this graph is showing. If I have, let's say, a block of water, and my block of water is frozen, -20, okay? And then I begin to raise that temperature. You notice how this line is perfectly straight? In other words, for every 1 degree of temperature that the ice goes up, I had to put in a specific amount of BTUs. All right? Heat added in BTUs from -20. So by here, I put in 26 BTUs to take this water from -20 degrees all the way up to 32 degrees. In other words, that's approximately 1/2 of a BTU per degree. I went from -20 to 32. That's an increase of 52, right? Yet it only took me 26 BTUs. To go from 32 degrees frozen to 32 degrees liquid, I have now spent 170 BTUs. 170 minus 26, I'm looking at 144. I spent 288 times more energy to make that 1 degree temperature change than the degree above it or the degree below it. Why? Because of phase change. So I have a block of ice and I put it in my cooler. It's not the same as saying I've got cold water and put in there. That ice has to absorb so dramatically much more heat to phase change. Once it's turned to a liquid, it's not doing you as much good, guys. That's the reason that you drain your cooler out throughout the day to get the liquid out of it, because that liquid's not doing you very much good. It's the phase change of the ice into that liquid that is actually keeping the products in that cooler cold. Just the same way with the dry ice, except instead of phase changing from a solid to a liquid, it's actually phase changing from a solid to a gas. Well, let's look at water on the gas. So once again, I have a linear heating line. In other words, for every 1 degree that I went up, okay, I went up 180 degrees in BTUs. You notice here, and I went from 180 degrees here. So suddenly, I am now at a 1-to-1 ratio. As a liquid, this water will absorb 1 BTU for every 1 degree in temperature that we raised. All right, I get all the way up to 212 degrees, and now I want to turn this liquid into a solid. This liquid into a gas. To go from 212 degrees liquid to 212 degrees steam took me an additional 970 BTUs of energy. That phase change is astronomical. It's the reason your swimming pool, it loses 90% of its heat through evaporation. If you put a pool cover on your pool, you'll get 3 weeks more, 4 weeks more use out of your pool in the fall, and 3 weeks more use earlier out of it in the spring, just from covering it. Evaporative losses are huge. Right? To phase change water from a liquid into a gas takes 970 times more energy than it took to raise that same amount of liquid by 1 degree. Questions on what phase change are or why phase change takes so much energy? So phase change is an important concept. We have sensible heat, and then we have what's called latent heat. These are the sensible ones. They make sense. They're aligned. You put in 1 BTU, you get 1 degree. And can you imagine the scientists trying to figure out this crazy thing right here? Like, dude, to get it to go from 32 degrees frozen to 33 degrees liquid took me like 144 times the energy. That just doesn't make any sense. So they call that latent heat. Can anybody think of how we could apply that massive amount of energy that it takes to phase change to keeping our homes more comfortable or more energy efficient? No? There's some really cool concepts that have come out since the 70s and 80s. In the 1970s, we had an event that was called the energy crisis or the oil crisis. None of you guys were alive for that. I wasn't really even alive for it. I remember it happening in the early 80s, having gas lines that were really long. But suddenly in the 70s, we realized, oh, wait a minute. We primarily use fossil fuels for energy, and we are going to run out of fossil fuels. In fact, that's the first time in our history that we began to use them faster than we could produce them, which made the price go up, and it made everybody freak out about energy conservation. So since then, both the government and private individuals and companies, for-profit companies, have spent a lot of thought into making our homes, more energy efficient, our lives more comfortable in the process. And one of the things that they found is phase change liquids to be a big benefit to do that. What temperature do you like to keep your home in the summertime? If you set the thermostat, what would you set it at? 75. Anybody keep it in the 60s? 65. I suddenly have a 10-degree difference between how Brian would like it and how Randy would like it. Now let's flip it. Wintertime. What temperature do you want your home in the wintertime? 60? What temperature would you want your home in the wintertime? Probably 75. So isn't it crazy to say it's colder outside in the wintertime, but Brian wants his home 10 degrees warmer during that time of the year than in the summertime when it's hot outside? No, you're okay. That's the reality of what we want. That's most Americans, okay? We want it warmer inside in the wintertime, so we come into warmth and comfort. We want it cooler in the summertime, so we come into cool and comfort. it'd be very easy for me to come up here and say, hey, you all need to live your patterns based on what he wants, because his home is going to use 30 to 40% less electricity than Brian's home. And then I'm going to walk out and you're going to go right back and set your thermostat where you wanted it. Instead, I need to be able to build a home for you, specifically a custom home for you, that uses very little energy to keep your home comfortable. Well, the Chinese have an amazing product. It's not legal in the United States yet, but it is phase change sheetrock. And it is even programmable based on your particular temperature desire. I love a temperature of approximately 70 degrees. In the wintertime, it's plenty warm for me. In the summertime, it's plenty cool for me. So I can buy 70-degree phase change sheetrock. It means my sheetrock turns to a liquid and cools out on the floor. No. What it means is that there's tiny bubbles inside of the sheetrock that are phase change glauber salts. Basically, it's a salt that if you mix it at the right consistency, you can change its phase change temperature. So you could have your salt mixed to where it would phase change at 75 degrees. I can have mine phase change at 70 degrees. He could have his change at 65 degrees. And, Cameron could have his at 60 degrees. And basically, you think about it. During the daytime, my home starts to get hot, but my sheetrock absorbs a massive amount of that heat, keeping it cool, and phase changes all of its little bubbles into liquids. It kept me from having to use air conditioning to do that. Now, come nighttime, it's cold outside. It starts to cool my home down, but those glauber salts are all liquids. In order to get them to turn back into solids, they have to release a massive amount of heat, therefore keeping my home warm. It looks just like this. It acts just like this. It might cost a little more up front, but if it saves you a couple dollars every year on your energy bill for each sheet that you install, that extra cost ends up paying for itself. What's more important is we don't have to ask people to make significant sacrifices to their quality of life. You can still have it warm in your home in the wintertime. You can still have it cool in your home in the summertime, and you don't have to use a massive amount of energy as long as you designed and planned for the appropriate materials for the appropriate climate. Phase change is an important part of that, and the specific heat of materials is important. Because if I can use things like water walls in my home, I can retain and store more energy in that water than the same quantity of masonry. Right? And so understanding which of these materials will capture and store the energy is very important. So thermal expansion. What happens when things get hot? Yes, sir. Yep. Sure. We don't know what glauber salts would add into the air quality or what happens if your 3-year-old chews on that sheetrock. So it has not been approved by the IBC, the International Building Code, for installation in the United States yet. Do you want the real reason? That's the on-paper reason. The real reason is American companies don't own the technology, so we can't legally manufacture it ourselves and make a profit on it. So our industry will continue to want it to be proven unsafe until they can capitalize on that. We are not motivated by, hey, this is a great product that's better for the environment. We're motivated most of the time by our industry. Our economy needs to make sure that it's not going to suffer for this higher quality product entering our market. An excellent example of it is PEX piping. We've had PEX piping in the world since the 70s. All of Europe's been using it since the 80s. When PEX piping freezes, it doesn't break. Okay, there's no off-gassing from it. There's no buildup from it. Yet it was illegal until the 90s, and it was only until California stepped out on a limb and made it legal that the American companies were like, well, we can't keep it out anymore. Let's start making our own PEX. And today, not only is it legal, but it is the expected residential home plumbing system for the United States now. I truly believe that we will have phase change building materials within 20 years on our market. They've already got them in foreign countries that have lower environmental and long-term testing regulations. So one of the things is also VOCs, volatile organic compounds. When you put any building material in your home that's got a glue in it, that glue breaks down over time and off gases. It's been proven many VOCs lead to cancer. They're carcinogens. And so until the proper studies have been done, like, hey, we're going to put your sheetrock in this home, we're going to close it up in an airtight space for 2 or 3 years, and we're going to measure the VOCs, it's hard to get regulatory body approval for those new products. Did that answer your question? Awesome. Any other questions over those phase change style of products? No? All right. So thermal expansion. When things get hot, they get bigger. And now sometimes this can be a weird thing to understand. And so I like to put a hole inside of another product to expand what gets bigger. Logically, you'd think that the whole thing would get bigger so that this hole would get smaller. No, the whole thing gets bigger, including the hole in the middle of the thing. So let's look at it this way. You have a backhoe, and you have a giant component that is bolted to the frame of that backhoe. Whenever it was put on, it was brand new, it was shiny, there was no rust or corrosion, and it was put on with a tool that put it on to high impact. I got to replace this part. I got to break that loose. Guys, my buck 50 wet ain't breaking a lot of big bolts loose. I don't have the weight and the strength to do it. So what I have to do is take a torch and heat the outside component. That gets bigger. The hole gets bigger. The bolt I try to keep as cool as possible so it stays smaller. Therefore, there's less friction and I can break that bolt loose. There's also this theory of making things really, really tight. When I put that back in, if I keep that bolt cold, like literally I'll put it in a deep freeze, okay, dry ice, and then I get this really hot. When my skinny butt, puts as much torque on it as I can, when that cools down, it's going to shrink and it's going to physically lock that bolt into place. All right? Heat can be just as good as Loctite in certain situations. If you have a 100-foot long 10-gauge copper wire, anybody want to guess on how much it could shrink or swell? In other words, get longer or shorter based on our standard outdoor temperatures here? Up to 4 inches. Yeah. So you can have 4 inches shorter of a wire in winter time as in summertime. So I make this, it looks really pretty. There's no extra ends. It sticks right up into my connection and it attaches. Wintertime, plop, it pulls loose. If this is a power providing wire, now I have a short. Now I have a fire. Now I have a lawsuit. Okay, so we solve this problem with simple wire loops. My wire runs along, I do a loop, and my wire continues to run along. I put a zip tie here, here, and here, and as this wire shrinks, it will pull its length out of the loop. All right? If you don't know about a problem, it's hard to solve it. Thermal expansion and contraction can be a problem. All right. So mechanics for heat transfer. We've already talked about conduction, convection, and radiation. I think that we're probably going to call it here as we begin. When we pick up on Wednesday, we're going to be talking about R values and U values. All right. For those of you who are in the video, I'm going to go ahead and end it. Thank you for joining us.